Excellent. So yeah, we can start. Yeah, welcome to Applied and Computational Maths Seminar. This week we have Sasha Ardaseva from the Niels Bohr Institute in Copenhagen. And Sasha started out her academic career in St Andrews, and then she's been in Oxford, and she's currently actually just finished up a 2-year postdoc in Copenhagen, but it started a Marie Curie Fellowship, which will probably bring her back to Oxford as well. So yeah, this is her connections, and she's going to talk to us today about interactive, active matter. So yeah.
Hello everyone, thank you for inviting me here. And the title of my topic is very general, mainly because there'll be 2 parts to my talk. My main interest is how do cells interact mechanically with their surroundings, whether it would be other cells or it would be the substrates they're on. And I'll first just briefly introduce why we care about cells and mechanical interactions between the cells. And then I'll just give 2 examples of different modeling frameworks that we use to study this. First would be a very detailed way to model cells such that we know what happens exactly at the interfaces of the cell. And the second would be more coarse-grained continuum approach to modeling biphasic fluids. And this will be also, I'll show some experimental data that we work with. So to start with, cells behave, like if you look at cells, they have very complex behavior. Cells if we think about monolayers, cells extract traction forces, and this is how they move. And if they're together, they start showing some patterns and interesting alignments. You also get some proliferation happening, so it's all very dynamic. And we know that genetics, also biochemical signaling plays important role, but also mechanics. And it is important to understand how this all works, because then we have some biological problems where cells actually move, and it is crucial that they move correctly. And for example, during development, or wound healing, or cancer metastasis, where cells actually invade a healthy tissue and then travel and go into another organs. There are various ways to approach this problem, and since I'm in a physics department in Copenhagen University, we approach it from a physics perspective. We make similarities between biological materials with liquid crystals. So liquid crystals are materials that are in between solids and crystals. They have orientational order, but they lack positional order. And one type of liquid crystals are pneumatics. These are elongated rods that under certain conditions align in a certain direction, as shown in the diagram, and they form this pneumatic order. And this is very similar, for example, to bacteria. They're also elongated. But we are dealing with active systems. So our cells, they move, they consume energy, and so on. Therefore, we approach this as that cells take energy from their surroundings and convert it into mechanical work. Therefore, what I'm working with is called active pneumatics. And active pneumatics has some features that have been studied. These are just some examples of how this theory can be applied to different systems, like bacteria. I already mentioned that they are elongated naturally, so there is an obvious connection to the pneumatics. You can also have like fibroblasts, which are also a bit elongated, but we also see that epithelial cells that are more circular and round, they also exhibit same behavior as active pneumatics. And what is specific to active pneumatics is that you have topological defects. So if you look at the orientation of particles, there'll be areas where you have singularities in the orientation field. And these we call topological defects. In regular liquid crystals, nothing moves, everything is passive. But if we have active entities, they're out of equilibrium, so they will eventually, if activity is high enough, will lead to so-called active turbulence. This is a regime where you have chaotic flows with jets and swirls, and interestingly, the topological defects also become motile. In my talk, I'll be only talking about 2D system of active nematics, and in this system, there are only two types of topological defects. First is a comet-like or plus-half defect. These defects are motile, so they have self-propulsion. And the other type is a trefoil-like defect, or minus-half, and these defects are stationary. They don't move. They always come in pair, such that on average, the topological charge of the system is 0. And depending on the type of active stress, whether the particles are pushers or pullers, this defect can either move along the head or backwards.
Sorry, what do the numbers mean? Like plus and
numbers
minus
are
a half?
charge. So if you
like a dipole approximately?
no. It's if you look at the orientation, how much it will change if you go around the circle.
Oh,
So here
okay.
it's pi or 2 change in the direction, and there is minus. But there are full integer defects with the vortices
Okay.
and anti-vortices.
Okay.
Recently, there have been lots of studies trying to understand what is the role of these topological defects in actual biological setups. And they turn out to be quite important. For example, if you have a cell monolayer, plus-half defect will coincide with the areas where the cell will be extruded from the tissue because of the accumulation of stress on the top of, on the head of the plus-half comet-like defect. Another example is these experiments where they took a growing animal called Hydra, and they saw that the location of where the limb will be forming coincided with the full integer defect on the surface of this animal. So, and what in our group we do a lot is to try to model it and study it and work with experimentalists. But we need ways to model these things. And the obvious thing to start is to look at the continuum with the crystal theory. This is our continuum models. So there are no cell heterogeneity. We cannot understand, we don't have information about what happens at the interface between the cells. Another way to study this are self-propelled point particle models, but these are usually suitable for systems far from the dilute limit. And usually models add some polar driving, so some self-propulsion of the particles. But what I'm going to talk now is a bit more detailed model based on a phase field formulation, where we model each cell individually, so individual-based cell model. So for each cell, we define a phase field phi I. It can range between 0 and 1. 1 corresponds to the interior of the cell and 0 to the exterior of the cell. And if we have n particles, we'll have n phi fields. And we have an equation governing the dynamics of phi. We have an affection term, and the free energy, which will set the interface of the system. And if you have many particles, we'll have many equations that we need to solve. Our free energy here is the most minimalistic we could come up with. It has 3 terms. So the first term is Canhilliard free energy. Essentially, it has a double wall potential, setting the 2 minima at 0 and 1, with a boundary between the cell and outside of the cell occurring at 0.5. The second term sets straightforward area. We want cells to be more or less spherical or circular in 2D setup. And the third term is repulsion term, making sure that the cells don't overlap too much. Yeah, so we then assume an ODAM system. So we have a substrate friction. So we model a cell monolayer on top of a substrate. It also have some friction with it, and it balances the forces that act on the cell's interface. You can add more to this model by, for example, considering adhesion between cells or adhesion between cell and substrate, and this will go into the free energy formulation. And we incorporate the microscopic interface forces through the stress tensor sigma, and yeah, since we want to include some link to the liquid crystal theory, we have to introduce the nematics into it. And to do so, we define a director of each cell. So the where the cell is elongated, for example, if you want to think experimentally how you would define that. And we do this by introducing a nematic tensor Q. And so then our tissue stress becomes like this. We have two components. We have pressure that cells exert on each other, and we have activity term. So this is what gives cells, so this is the conversion from energy from outside into a mechanical movement. And the parameter zeta is the strength of this activity. And depending on the sign of zeta, you would have either extensile or contractile particles, whether they are pushers or pullers.
And the nematic tensor is traceless.
Yes, yeah, symmetric traceless. And we want to also, right now we only evolve cells, we also want to evolve the director of each cell. And to do so, we write an equation for the orientation angle, so angle of the director. And we assign it to have two terms, so two torques. The first torque aligns the director to the tissue nematic tensor, so it induces elastic restoring force, and the second one rotates the director with the local vorticity. So our director interacts with the flows and what's happening around it. And if we do simulations, this is example how it looks. Here this is example of 100 by 100 domain, but all the next simulation will be on 400 by 400 grid points with roughly 1,000 cells. We initially place the cells randomly on a grid, let them relax, and I'll probably play again. And this is just we plot phase field with the contours. And in this plot, we course grade the director, so the orientation of the cells. So you can see you start having some balance play deformations, and then formation of topological defects. You can see this is, for example, plus half, it moves. This is minus half, it's more or less stationary. And I think the goal for this work was to make sure that what we have modeled here agrees with the continuum theory. So to do so, we first of all try to understand what happens at every stage of the simulation. So at the beginning, after some time, you will start seeing this bend and splay stabilities. Depending on the activity sign, the system will be more prone to either one or the other. And you can see as the time progresses, we start having these walls where the order is broken. Then, as the time progresses, along the walls, you will start having pairs of topological defects appearing. Plus halves will move away, minus halves will be staying there. And importantly, if you look at different activity strengths, as you increase activity, the time to the formation of the first pair of topological defects will decrease exponentially, which is an agreement with the continuum theory. We further then can characterize what happens to these defects. And we can see that, again, we measure everything comparing to the activity strength, that as we increase activity, you would have more defects, so defect density will increase, the rate of creation of topological defects will also increase. But then, interestingly, if we measure the average velocity of the defects, what we will see that if you have low activities, then we have the fact that plus half defects have faster, larger velocities, and minus half have smaller velocity, which is in agreement with what we know, that plus halves are motile, minus halves are non-motile defects. But as we increase the activities in our model, we no longer see the difference. So if we measure the diffusion exponent, actually both defects types become diffusive, which is observed in some experiments, but not in many. So this was an interesting difference between our model and the continuum. Furthermore, we can look at average qualities of the defect. So we can average the director, and it looks like comets in the truffle, which is what we want. We can also average the velocity flow fields around the defect, and we can correctly capture the fact that when you have extensile, the defect moves one way. When you have contractile system, the defect moves another way. We can also look at the velocities and just characterize the flows. So here we have measured average velocities for different values of activities, and we know that the total velocity in the system with periodic boundary conditions should be 0, and it is 0 here, and then which is what we expect. And I think the most interesting part here was that we took the divergence. Since it's an incompressible model, we expect divergence, a non-zero divergence, but this was not the case at higher activities, where the divergence actually deviated from 0. And these led to us observing that in our simulations, sometimes we can observe gaps between the cells. So
that's physical, or?
It is physical, yeah. So, for example, here, everything, it's a confluent monolayer, cells all touch each other nicely, but then here, you can see that there are lots of heterogeneity in density. There are regions where cells squish each other. There are areas where you will just have no cells at all.
Do you have any volume conservation?
Yes. They're just
compressing.
Yeah.
Oh, they are. Okay.
Yeah, and we try to quantify this. So we measured the amount of empty space in the simulation, and what we saw that the amount of gaps increases with the activity, but also with the elastic constant that we can change.
So what's that constant? What's that the elastic constant?
It comes into the free energy. So whether cells are more elastic
so
or not.
what does it represent?
Whether cells are squishable, therefore more deformable or less deformable.
Compressibility.
Yeah.
It's a kind of bulk motion, is it?
Yeah. And you can see that also in these different conditions, cells will have on average different shapes. So we looked at the area or areas of cells in simulations, and when you don't have gaps, cells are more or less hexagonal. Whereas when you introduce higher activities, cells become a bit more circular. Yeah, and there are experiments where they actually see these gaps in monolayers, especially like cancer cell monolayers. There are some studies, but we haven't really gone into exploring it and applying this and trying to understand. We thought these gaps would correlate with the topological defects because there are studies on bacteria where they suggest that plus half defects, you would get accumulation of fake of tissue there, whereas minus half will have some empty space with them. But we didn't find any correlation between topological defects and gaps.
Is there any spatial correlation? I mean, there's no kind of compression waves or anything?
No.
It's all just random, yeah, it's just white noise.
Yeah. So, to summarize, the point of this part was just to introduce the framework. We have developed a very detailed model where we know what happens at the interface of the cell for every of it. Our model is the most simple we can get in order to reproduce the active thematic continuum theory. We more or less capture well the behavior for both extensile and contractile systems, and we also observe spontaneous formation of gaps, which we did not expect. And we can further use this model to do some other further studies and applications to biological problems. For example, here is we did some work where we have collaborators who look at the extrusions, basal versus apical extrusions in cell monolayers. And here we studied how the contractility, so the cells exert contractile forces on the substrate, how this affects whether cells will go up or they will go down. We also included adhesion here and looked at the interplay between contractility, cell-cell, and cell-substrate adhesions. And this is a work in progress. We have also extended the model into 3D, so we can model several layers of cells in 3D, and this was done by another postdoc in the group, Sasha. And the project I am currently working as part of my Marie Curie is this one, where we, instead of having cell on solid substrates, we put them on soft substrates. We have experimental data suggesting that, well, if you place a cell on something soft, it will create wrinkles in the substrate. And if you put two cells in a substrate, they will feel these wrinkles. So they will know that there is someone somewhere nearby. And what we see that some cell types, they move towards each other along the wrinkles. So there is some kind of communication going on via this substrate deformation. And this is currently what I'm working on. So we sometimes, all these detailed models are very nice, but they're computationally expensive, very long to run, and to analyze all the data. So sometimes it's better to have a bit more coarse-grained approach and look at continuum models. And here I'm going to present continuum liquid crystal model, where we look at the interaction between the two fluids. And this is done in collaboration with experimental people in Sheffield who work on bacteria. So there'll be a bit of introduction to that. So these bacterial communities, not only, you can see it's an example cancer, they're very diverse. You have cells exist in various environments, they're dynamic, they vary spatially, and cells have to adapt to that. And one way would be to adapt what types of food they prefer. For example, these experiments, they're done on cells with different metabolic characteristics, and the patterns are very pretty. You can do a lot of nice experiments here, but the cells can also differ in their motilities, so how they move, whether they move fast or slow. And here just example of some simulations where they put two different bacteria strains. They vary with their motilities, and they look how the front propagates, whether you have some leader-follower behavior. And our collaborators, Mike and Ollie, they work with the same bacteria. So they have a faster bacteria, so they're wild type. I think it's Pseudomonas aeruginosa. And they have another strain, PLH, which can move faster because they have probably more highlight. And when in this experiment, they made them race and look to see who will lead, who will follow. In our case, they just put them all in a box or on a plate, and they wanted to see how these two strains behave when they're mixed, whether they will phase segregate completely or they will be mixed. And yeah, what they observe is that they don't phase segregate completely. Instead, they observe the formation of small domains, so roughly on the size of 10 bacteria. And these small domains, they keep getting created, annihilated, so it's a very, very dynamic process. And they made a repeated experiment to make sure that it arises from the difference in motility. So they took just one strain and they colored them in different, labeled them with different colors. And this segregation was not visible when you only had one strain. So this had to come from the fact that the strains differ in their motilities. But since what they observed was quite dynamic, they thought maybe it has something to do with topological defects, because topological defects, they are created, annihilated, and it's also a dynamic process. So they identified the defects. So red ones are comet-like defects, they're motile, and minus halves are in blue there. And what they looked is they looked at average concentrations around the defect. So here you have positive and negative defects. These are for two different types of experiments. And what they saw is that plus half defects were enriched with more active strains of bacteria, whereas minus half defects, so the non-motile ones, were enriched with slower strain. And in order to try to understand why this happens, they did some simulation with the SPR models, the self-propelled rod simulations, where cells are modeled as stiff rods of mutually repulsive potentials, and these rods have self-propulsion force. This is an example of one simulation where you have yellow particles which are active and blue particles which are passive, so they simplify it to the passive-active system. And you see, again, defects, and similar picture. Plus half defects are enriched with active particles, minus half enriched with passive particles. And if they took the divergence of the flow fields around the defects, and what they saw that this enrichment was gradual. So originally, since we have active-passive defects, all defects were created in the active phase. And then during the time of the simulation, then slowly plus halves will accumulate active phase and minus halves passive phase. One explanation we thought of that could be is the fact that there might be some kind of anisotropic friction going on there. And it is essentially that perpendicular cells experience greater frictional resistance to forward motion relative to the parallel cells. And this is because there have been some experiments with where they had only one type of bacterium, and they saw that the areas where plus halves were more, the density around the plus halves was bigger than the density around the minus halves. But if you take, so in order to study, they looked at different frictional anisotropy values, and they looked at average charge of the active phase. So they looked at all the where the active fluid particles are, and they just calculated the charge. So, but what they saw is that frictional anisotropy does not affect that. So this was not what was causing this phenomenon. So then we developed another type of a model, continuum one, and this work has been done with Chaitanya and Sumesh. Chaitanya at that time was a PhD student who did most of the simulations. And essentially in our model we we wanted to simulate interaction between the two fluids. One is more active, one is less active. And to distinguish the two fluids, we defined phi, which is the density of fluid. It can range between 0 and 1. We also define a nematic order, so it's the same as we had before in the individual-based model. Q, which is a symmetric traceless tensor. And we define the free energy to have 4 terms. The first 2 refer to the phi, and the other 2 refer to the liquid crystal features. So they work on the nematic order. So these 2 terms, the first one is the double wall potential. So we have minima at 0 and 1, so we have one or the other fluid. And the second term penalizes gradient in phi. And we can use these coefficients A and K to define the surface tension between the two fluids. In experiments and in this PR model, the surface tension is 0, but we can also explore the scenarios when this is not the case. So we have convection diffusion equations to govern the dynamics of phi and Q. These terms arrive from the liquid crystal theory. And we also have Navier-Stokes equation for the velocity. In the momentum equation, we have these 2 terms. The first is has a stress tensor, which is similar to what we had in the individual-based model. An important bit here is that we again add activity, so the dipolar activity, to make the system out of equilibrium. Zeta is the activity strength, and since we have 2 fluids of different motilities, the zeta is phi dependent. So if phi is less than 0.5, if it's fluid 1, you will have zeta A, and you'll have zeta B if it's another fluid. We also add anisotropic friction to make sure that our model is consistent with what we saw in this PR, and we want to check whether here anisotropic friction would do something. So this is an example of how the simulation looks like. We start with a random initial conditions, and our fluid separates into 2. So yellow is more active fluid, and red is less active fluid. So, and you will start having topological defects when the system goes into active turbulent regime. We also repeated all of this with a passive active system, and all the results I'm showing here are they do hold for active passives as well. So to try to quantify it, we calculated the average charge of more active fluids, so the yellow one. And what we saw is that indeed in some parameter regime, we see that more active phase gets positively charged. So there are more plus half defects in yellow region than in the red region. So this was in agreement with experiments and SPR model. But what we saw is that in some parameter regime, when the difference in the activity between the two fluids was small enough, the more active fluid will be charged negatively. So there will be more minus half defects in the yellow regions. And to try to explain that, we had a lot of painful hours looking at simulations and trying to see what the defects actually are doing. And we identified two scenarios. So this is just a schematic picture. If you imagine you have a more active fluid in yellow surrounded by less active fluid in blue, and you put a pair of defects in more active fluids, there are two options. First, we saw that the plus half defect would carry along the more active fluid, so it will move with it, leaving minus half in a passive fluid. This way, more active is positively charged and less active is negatively charged. Another option was that the plus half defect was too active, too motile, that it escaped the more active fluid. So at the end, we would have that the less active fluid would be positively charged, whereas more active fluid would be charged negatively. And this is just an example of simulations of these both two cases, where this red arrow follows the defect as it escapes from more active into less active, and here is the minus half in this scenario where the more active fluid just escapes under it. So these two options, they occur in all types of simulations independent of parameters. The only difference is the frequency at which these events occur. So when you have big difference in activities, these events are more common. Whereas you have smaller difference in activities, these events occur more often, and hence you would get this this picture where you have switch between charges of the more active fluid. So all previous simulations and results have been done on the case where you have zero surface tension, because it was closest to the experiments and SPR modeling. But since we have an option to turn it on, we did explore what happens when the two fluids have non-zero surface tension between them. And here, essentially, is the Pice diagram where we have differences in activity and values of surface tension along the x-axis. And this switch between positive to negative charged fluid, more active fluid, it still holds when you turn on the surface tension. In fact, it becomes more pronounced. And we also looked at the anisotropic friction. It's not activity there, actually friction. And we confirmed what SPR model saw, that anisotropic friction is not doing anything to this charge separation, and that this must come from the fact that the two strains are different in their mentalities. So to summarize, this was an example of an very interdisciplinary project we're doing. We showed that this difference in motilities promotes the unmixing between different bacteria strains. We saw that histological defects are enriched with more active strains, whereas -halves are enriched with less active strains. And we developed two types of models that were able to capture what we saw experimentally and give us some kind of explanation of why we observe these differences between the topological defects. And this is currently what we are writing up. So with this, I will thank you for listening, and I'll thank the people that were involved in both parts. The first part was Roman, who wrote and optimized the code for the individual-based model. Amin is my supervisor. And for the part 2, Ollie and Mac were the people who did experiments. And then Chaitanya, Sumesh, Amin, and me were responsible for the theory part. And thank you to all my group members.
Excellent, thank you. Do we have any questions from the audience here?
Why do you think the liquid crystal, the nematic liquid crystal, is the most appropriate model for cells motility?
I wouldn't say it's most appropriate.
The one you're using.
I think, well, I wouldn't say it's the only one. It's fascinating how accurately you can capture.
It works.
It works because if we compare with like velocities and just visually the qualitative behavior of cells, it can capture very well some of the systems. It will not be, might not capture some more complicated, like individual cell moving through. You would need a different level of like what we had in the first part, but it's surprisingly well captured. Is what I see.
With the nematic liquid crystal, I suspect you have a great dependency on temperature and stuff like that. Do you have anything like it?
I think it's kind of encoded into free energy formulation. I'm not familiar with all the duration of the liquid crystal model, so I cannot comment on that. But I think how we define the activity of the particle, because we can also in here we just impose the dipolar activity, but we can also add noise to it, and this would correspond to raising temperature.
Yeah, I mean, I'm trying to think whether there is any analogy between liquid crystal and cells, but movement in terms of nematic isotropic transition when nematic is ordered, isotropic is disordered.
Yeah. I think there are. I'm maybe not the best person to explain that, but
yes, great talk. I just want to understand both the models a bit better. In the first one, you modeled the cells without any diffusion, so they're located at like the location they are in. There's no diffusion of the cells, so you only model their orientation change, right?
Not only. There's also velocity acting on each cell, but as a whole, so there is advection term as well.
Advection term as well, right? So you have the free energy term, and you use that to calculate the forces on each cell. And does that then give you the torque on the cells, which gives you the orientation change?
So yeah, the change in orientation comes from the surrounding flows, so from the flow that are around the cell.
Right. And in the second model, you have two kinds. You mentioned two kinds of fluids. Could you explain this free energy term for the second model?
This one.
Yeah.
Yeah. So essentially, we wanted to this term separate that there are two fluids. You have phi equal 0, one fluid, and phi equal 1, another fluid. This makes sure that there is essentially penalizes gradient in phi. So these refer to the unmixing of the two fluids. These they account for the movement of the director, so of the orientation. Yeah.
So in that first part, when you have the discrete system, so you have a background Newtonian fluid, presumably, that you also said, you have a coupling to that. You say the background flow that's working on the particles. I mean, how do you?
Well, if cells, there is no liquid.
So they're in a background, like in a vacuum.
Yeah. But they push on each other, and this is how you would get.
Okay, so that's that. In your pneumatic evolution equation, you've got the torque term, and then you've got this omega, the rotation vector. I mean,
it comes from all the cells, so we calculate from the cells.
Okay.
All the velocities, and then feed into the director update.
Okay. Why would that not already be accommodated by the torque?
Which torque you
mean? Maybe you can get the equations like d phi I by dt.
So, I mean here.
Well, when this gets worked out, I guess.
It goes. I think it is actually from you calculate from these velocities and you feed into the director. Yeah.
Okay, so it's kind of like you almost coarse-grain the bulk background velocity, and then you put it back in. Okay, so it's kind of an in-between a discrete and a continuum model.
Yeah.
That's interesting. And so there really is two-way coupling with that, because the way the particle responds to that background bulk flow vorticity does actually contribute itself to the background bulk flow vorticity.
There is another way to model the whole director thing, and in this, here we just impose that there is director and it evolves. Another way is to look at the shape and say where the cell, even like the axis of elongation, this is your director. So you don't then have this extra equation. This is just a way to make it closer to the continuum theory.
Okay, so it's
and make it kind of
intermediary. Okay, now it makes sense.
Can I see again the energy where you had your elastic modulus? I missed that, where it appeared for the first time and defined it.
And I think it's
energy.
The behaviours here. The elasticity.
So it's gamma, is it?
Yeah.
Oh, yeah. And you don't know what it measures. It affects the compressibility, does it?
Yes.
It must be a bulk modulus.
Yeah.
Bulk elasticity. Okay. So is the compressibility going up or down rated gamma?
I would need to check that. I don't remember that in my head.
The pictures. You have
so higher gamma.
It's more compressible when gamma decreases.
Yeah.
Yeah, it must be the bulk modulus. Yeah. Okay. Yeah, makes sense.
Well, if we have any more, we can ask Sasha over coffee and the first thank you again.
Yeah. And so there's brownie.
Important question.